Good afternoon, everyone. Today is the last Atmos seminar of 2025. We have the pleasure of welcome Professor Eduardo Filipe. Professor Filipe holds a PhD in cryogenic thermodynamics, having worked with mixtures of simple fluids such as light alkanes, plethora alkanes, and rare gases to test molecular-based statistical mechanics theories. He currently teaches chemical thermodynamics and molecular simulations at the Chemical Engineer Department of Instituto Superior Técnico, University of Lisbon, Portugal. He also leads a research group at the same institution, specialization in high accuracy measures of equilibrium, surface, and transport properties of fluids. Research focuses on the experimental development and modeling of complex fluids with applications in the biomedical and environmental fields. So once again, welcome, Professor Filipe. Thank you so much for accepting the invitation. It's a pleasure to have you here with us. Please feel free to start your presentation.
We will talk about soft matter, and soft matter which is in fact fluorinated, but not fully fluorinated. An alternative title would be how the mutual phobicity between hydrogenated and fluorinated chains determines the organization of supramolecular structures. This title is already a little bit more specific and probably a bit more informative to you. Anyway, I think it's clear that we will talk about self-assembly. And in fact, self-assembly is, for me, in my opinion, one of the most fascinating subjects in science. And I have been, it's one of my key subjects since I was very young. So it's a pleasure for me to have worked in self-assembly for a couple of years now. In classic self-assembly, it requires to have some sort of asymmetry at the molecular level. Specifically at the intermolecular potential. The classic example is a molecule which will have a hydrogenated chain, meaning hydrophobic, and then a group which is polar or ionic and which is obviously hydrophilic. However, these are the basic building blocks in classical soft matter. However, there is another type of hydrophobic chains which are perfluorinated chains. They are also apolar, so in many ways they are very similar to hydrogenated, but with them we can also, by adding a polar or ionic group, we can also build amphiphilic substances. In fact, perfluorinated amphiphiles are well known, and they form, as the hydrogenated amphiphiles, they form all sorts of fluorinated supramolecular aggregates like micelles, vesicles, liquid crystals, and they have very interesting properties. They are much denser, viscous, more volatile. They're much more rigid than the hydrogenated chains, and they are also inert and biocompatible. Moreover, they dissolve small gaseous molecules very well, like oxygen, nitrogen, and CO2. They exhibit a very, very low surface tension of the order of 10 millinewton per mole, and they have an enhanced hydrophobicity. For this reason, they are very efficient surfactants, and they find applications in surface science, material science, and even in biomedical applications like liquid ventilation and blood substitutes. However, I think that the most interesting property of perfluorinated chains is the fact that although they are very hydrophobic, they also interact very weakly with hydrogenated chains. This is a case which is very interesting in my opinion, because we are in presence of apolar chains, both are apolar chains, which interact among each other by very similar dispersion forces. However, they are mutually phobic, as I will show you in a moment. When you try to mix an alkane and a perfluoroalkane, it's very probable that they will phase separate. Therefore, when we mix these two types of chains, it's very probable they will nanosegregate, although the intermolecular forces are very similar between the two. I like to think of these molecules as two fluids which are, although very similar, almost identical, in a way they don't like to interact each other. So the basic question, and this is probably the key idea for the rest of my talk, is how can we use this mutual phobicity between the hydrogenated and fluorinated chains to influence organization? And the answer is yes, we can do that. This can lead to compartmentalized micelles and other supramolecular structures, and hopefully for the rest of my talk I will present you a number of examples that we have been studying in my research group, in which the mutual phobicity between the hydrogenated and fluorinated chains can be used to influence organization and to build compartments within the supramolecular structures. There are 4 examples. In one of them, only dispersion forces are present. In a second example, the two types of chains will be also interacting through electrostatic forces, because we can introduce some ionic groups. In a third example, the two types of chains can interact through hydrogen bonding. And finally, in the fourth example, we will stick the two chains together, bonding them covalently to each other. In the first example, this is the classical example of mixtures of alkanes and perfluoroalkanes. When these mixtures started to be studied many decades ago, people were expecting that they could behave ideally because the two types of forces are very similar. And it was a surprise when they mixed, for example, hexane and perfluorohexane. It was a surprise that, in fact, in spite of being an almost ideal mixture, they phase separate. Hexane and perfluorohexane are immiscible in the liquid state, with a very convenient upper critical solution temperature around 20 degrees, and the excess properties, they are huge. For example, the excess volume of a mixture of hexane and perfluorohexane is one of the largest known for relatively simple substances, of the order of 5 cubic centimeters per mole. They also display large positive deviations to Raoult's law. And the question is, why is that? Since the intermolecular forces are so similar, where does this mutual phobicity comes from? And until now, we don't have an explanation for that. But we have worked on the subject for quite a while, and we made some important, I'm happy to say, although we didn't solve the problem, I think we have contributed with a number of new informations. One of them, for example, is this one. A few years ago, we proved that when an alkane is dissolved in a perfluoroalkane, it coils, which was not known until then. Coiling of chains is well known, but in systems in which there is hydrogen bondings, which is not the case. This is a case of coiling in a system where only dispersive forces exist. Another important contribution, I think, was to show that when you mix hydrogenated and fluorinated substances, the viscosity of the mixture drops enormously. We are preparing a new paper on the subject. And we have been not only measuring properties of mixtures of alkanes and perfluoroalkanes, but also modeling these mixtures with a number of different theories and approaches, in particular different versions of the SAFT theory. In this case, I'm presenting a paper published a few years ago with a group of George Jackson, in which we applied the SAFT gamma mi contribution approach to mixtures of alkanes and perfluoroalkanes. Today I would like to show you an approach that we have been using for quite some time, which I think is relatively unknown, but very interesting and informative. For some time, we have been using xenon, gaseous xenon, as a high-resolution NMR probe. The procedure is relatively simple. The fact is that the xenon atom is NMR active. The nucleus has a spin, therefore you can do NMR spectrum with it. And we have been dissolving gaseous xenon in a number of solvents, both alkanes, perfluoroalkane, alcohols, perfluorinated alcohols and their mixtures, and recorded the spectrum. The spectrum is very simple, it's just the peak. In this picture I'm showing three xenon NMR spectra. And as you can see, the range of chemical shift is huge, of the order of 200 ppm, which is very large. And this means that xenon is very sensitive to the medium in which it dissolves, and it shows where it's dissolved, and the peak changes accordingly. And this can be very informative about the groups present within the xenon coordination sphere. In this case, I'm showing the spectrum of xenon in hexane, this one, pentane, cyclopentane, neopentane. As you can see, the xenon atom can easily distinguish between all of them. And in the case of perfluorohexane, as you can see, the chemical shift drops to a much, much lower value. In fact, for us, it was a very logical step forward because we had been using xenon as a thermodynamic probe for a long time, and therefore using it as an NMR probe was a natural evolution of our work. In many ways, we think that xenon is the perfect probe because we had shown in the past that the xenon cross-section diameter is very similar to that of an alkane, and also that the dispersive energy of the xenon atoms is very similar to that of the alkanes. So in many ways, the idea is when you dissolve xenon in a liquid, the perturbation is minimum. So the probe is not affecting the structure of the medium, and therefore it can be considered the perfect probe. This is something that we had shown some years ago in this paper, at the time also with the group of George Jackson. So in the case of hexane and perfluorohexane, in this case I'm showing you the chemical shift of xenon in N-hexane and in perfluorohexane in the pure solvents as a function of temperature. And it drops a little bit simply because the temperature gets higher, the density of the liquids becomes smaller, and hence the chemical shift drops. But when you do the mixtures, as you can see, at below 25 degrees, the hexane and perfluorohexane phase separates, and the xenon NMR signal splits, and you get the phase diagram in good agreement with the experimental published phase diagram. Well, I thought this was a very elegant exercise, but the important information from my point of view is above the upper critical solution temperature. And in this plot, I'm showing you the experimental chemical shift, the dots, and in dashed lines, you can see the let's say, the expected chemical shift. And as you can see, they're not the same. So we were expecting the xenon chemical shift to be this value, and the actual chemical shift is different. This means that xenon is experiencing within its coordination sphere is experiencing a different environment than was expected, given the mole fraction, the composition of the solvent mixture. And from this difference, we can compute the true composition of the liquid in this mixture. So with xenon NMR, we have a tool that enables to determine the real composition, the real local composition in liquid mixtures. If we plot these differences as a function of temperature and composition, as you can see, xenon in the different mixtures is experiencing a difference in composition of the order of between 0.01 and 0.07 mole fraction, which is considerable. And as you can see, this increases. This is larger at around 0.5 composition, and these differences also increase as temperature decreases, meaning that we have, this is a proof of mutual segregation between hexane and perfluorohexane, and this segregation, as we approach the upper critical solution temperature, they increase. So what we are showing here is, for the first time, we could imply that indeed when you mix hexane and perfluorohexane, there is nanosegregation at at the molecular level, and xenon is able to sense this difference in composition, therefore this nanosegregation. We model these results with molecular dynamics. We used OPLS force field for the standard OPLS force field for alkanes and perfluoroalkanes. But in the case of the mixtures, we had to apply a reduction of 20% in the epsilon between the fluorine and hydrogen atoms, and an increase of 4% in the crossed diameter between the hydrogen and the fluorinated atoms. With these changes, we were able to reproduce both the excess enthalpy and the excess volume of this mixture, something that had not been done until this moment. The mutual phobicity between the two solvents has always been interpreted as weaker than expected interaction between the two molecules. So people, when modeling this mixture, in general, they would reduce the epsilon 1, 2, but they didn't realize that just by reducing epsilon 1, 2, they could increase the excess enthalpy in the direction of the experimental enthalpy, but the volume remains the same. And don't forget that the excess volume for this mixture is extremely high, of the order of 5 cubic centimeters per mole. And we realized that in order to reproduce the excess volume as well as the excess enthalpy, we also had to increase the sigma 1, 2 between the hydrogen and the fluorine atoms, which in physical terms tell us that it is the repulsion part of the repulsive part of the intermolecular potential that is playing an important role in the properties of these mixtures. In fact, the simulations could also show that the interactions, the probability of finding interactions between hexane and perfluorohexane are much lower than the like interactions between hexanes and perfluorohexane. So this is a proof of segregation between the two types of molecules in solution. And also, when we simulate the mixtures with a xenon atom in the simulation box, we see that the probability of xenon being in a medium enriched in hydrogenated groups, it's much higher than that, than the probability of finding xenon surrounded by fluorinated atoms. So this agrees with the experimental data, and this proves that in these simulations we can find domains which are richer in the hydrogenated component in which xenon prefers to be located. We were very happy with this result. This was some years ago, and in fact, the editors of PCCP considered this paper a hot article, and obviously were very happy with this nomination. Now, I move to the second example, in which we have studied mixtures of hydrogenated and perfluorinated ionic surfactants. Given what I said before, that the two types of chains are mutually phobic, when you dissolve two surfactants in which one has a hydrogenated chain, like in this case sodium dodecyl sulfate, with a surfactant with a fluorinated chain, a number of possibilities could be observed. They could form two types of fully miscible micelles. They could form fully miscible micelles. They could form partially miscible micelles, two types of micelles, but not pure. Or they could form a single type of micelle, but with intracellular segregation. This mixture had been studied experimentally by several groups, but in fact the experimental results were sometimes contradictory and inconclusive. So until very recently, people didn't know exactly what to think about the behavior of the mixture of these two surfactants. So we thought maybe with molecular dynamics we could give an answer to this problem, and this is what we observed. This is a simulation movie of a mixture of the two types, the hydrogenated and the fluorinated surfactant in aqueous solution. The water molecules have been erased for simplicity, and as you can see, only one type, you can immediately see that only one type of micelles is forming, which contains the two types of molecules. So we have a mixed micelle, but if you look closely, you can always distinguish that the micelle is more or less divided in two, forming what we like to call a Janus type micelle, in which it's more or less spherical, but intracellular, inside the micelle, we can find two compartments, one which is fluorinated and one which is hydrogenated. So doing an analysis of the aggregates, you can confirm that in fact the interactions between fluorinated and hydrogenated groups is much less probable than the interactions between the hydrogenated and between the fluorinated groups. And this means that of the four possibilities that I described earlier, this mixture tends to form Janus type micelle, as we like to call it, in which we find intracellular segregation. And I like also to see it as a micelle which has two different compartments, and we have shown, as I will show you in a bit, we have shown that we can dissolve different solutes, in particular small gaseous molecules, in each of the compartments according to the tendency of each molecule to dissolve. For example, methane will probably dissolve within the hydrogenated compartment, so will xenon, and small molecules like CF4 or even CO2 will tend to dissolve in the fluorinated part. This was published recently. This was done by a former PhD student of mine, Gonçalo Silva, and was recently published in Colloid and Interface Science. Inspired by and encouraged by these good results, we did more recently a systematic study in which we studied the influence of chain length and concentration. And in all cases, when we mix a hydrogenated surfactant with a fully fluorinated surfactant, we obtain the same type of result, a Janus type micelle with two types of compartments, one fluorinated and the other one hydrogenated. In this picture here, you can see already the two solutes were included in the simulation, and you can distinguish in the hydrogenated part a xenon atom, this brown one, and in the fluorinated compartment, you can distinguish a CF4 molecule dissolved in the core of this fluorinated compartment. We did another type of simulations in which now we studied a surfactant which has a chain which is semi-fluorinated, okay? And we changed the degree of fluorination of the chain. And this is the cases that we did from a fully hydrogenated surfactant to a fully hydrogenated surfactant to a fully fluorinated surfactant. And in this case, it was very interesting to find that we got not a Janus type micelle, but an onion type micelle, because these micelles display a fluorinated core surrounded by a hydrogenated corona. We even tried a more complicated situation in which the surfactant has a chain which has a hydrogenated segment followed by a fluorinated segment and finally a hydrogenated segment. And in this case, we obtained large micelles with a hydrogenated core surrounded by a fluorinated corona and surrounded by a second hydrogenated corona. So again, what we would like to call an onion type micelle. And we could show that we can dissolve different types of solutes depending on their tendency to dissolve in hydrogenated or fluorinated solvents. This was the work of Zé Santos Pereira, who this was the master thesis of Zé last year, and we were obviously very happy with this result that will be published very soon, hopefully. The third example that I would like to show you regards mixtures of hydrogenated and perfluorinated alcohols, in which now the two types of chains have groups, OH groups, which can interact strongly by hydrogen bonds, while the chains still interact through dispersive forces, which are, as we have shown, mutually phobic. We studied a number of mixtures of this type, and we need to understand that an alcohol is a very complex liquid in which the OH groups tend to form a network of hydrogen bonds because each OH group can form 2 hydrogen bonds. And they do it sequentially and giving rise to a network of hydrogen bonds, which is clearly seen in the figure that I'm showing you now. The thing is, if this happens in pure alcohols, both hydrogenated or fluorinated. The thing is, when you mix a fluorinated alcohol with a hydrogenated alcohol, now the hydrogen bond network still forms, but you have to realize that now you have 2 types of chains that also tend to segregate each other. And this gives rise to the following situation. In this case, I'm showing you the fluorinated domains. We have included the fluorinated chains, but also the hydrogenated chains form other types of domains which have segregated from the fluorinated ones. And in the final figure, I'm showing you the 3 types of domains. So in this complex mixture, you can distinguish the hydrophilic network of hydrogen bonded OH groups, and then 2 types of apolar domains, one which is hydrogenated in blue and one which is fluorinated in green. And this is the reason why we like to call these fluids as triphilic fluids, because they display 3 types of domains. Again, we are able to dissolve in these fluids different types of small molecules that will tend to go to the types of domains in which they feel better. For example, water obviously will tend to dissolve within the hydrogen bond network, while small alkane molecules will tend to dissolve in the hydrogenated domains, and small fluorinated molecules or CO2 will tend to dissolve in the fluorinated domains. We studied these mixtures again with xenon NMR spectroscopy, and this is the level of agreement that we find between the experimental results, which are the open dots, and those obtained from the MD simulations. So bringing together xenon NMR spectroscopy, the experimental spectra, with MD simulations, we have developed a methodology in which we can confirm the MD results, comparing the predicted local composition in the MD simulations, comparing with that obtained from the xenon NMR spectra. We were very happy with this result, and we think that there is a great potential to use xenon NMR spectroscopy to study the organization of even very complex liquid mixtures. This is part of the PhD thesis of Tiago Eusébio, that is now doing a postdoc with Felix Jovel in Tarragona, and was recently published in the Journal of Molecular Liquids. I don't have the time to go into detail, but it's interesting that this type of mixtures between alcohols and perfluoroalcohols also display a very interesting interfacial behavior. All these mixtures display minima in the surface tensile composition plots, and this is a rare phenomena called aneotrope, and all these mixtures display this behavior. We have not only measured this effect, but we have modeled this with, in this case, a version with a soft south theory in collaboration with a group of Lourdes Vega, and this was recently published in Journal of Molecular Liquids. This is part of the thesis of Diogo Machacar some years ago, and Teresa Pires is also working on this subject right now. A second paper will come out soon. A final example of a complex mixture involving a hydrogenated alcohol and a perfluorinated alcohol is the following. In this case, we have studied ternary mixtures of the two alcohols and water. As you can see, perfluoroheptane and water are immiscible, but as you add ethanol, the two components become miscible in this region. This would not be a very surprising results, because this is the usual behavior for many mixtures, but inspired by a very well-known case in which we do a similar mixture involving octanol instead of perfluoroheptanol, which is known to display the formation of micelles near the plate point of the mixture. So we wanted to see if in this case, using fluorinated alcohol, we could obtain, as with octanol, a fluorinated microemulsion in this region. Please understand that this is a case of a surfactant-free microemulsion, because we cannot consider the long chain alcohol as a surfactant. The chain is not very long, and we cannot call it a surfactant. And these surfactantless microemulsions are very useful in the case in which having a surfactant is not adequate for the purpose of the mixture. So in this case, not only we determined the phase diagram, but we studied the structure of the single phase region, in particular in this region close to the critical point of the mixture. And we measured the surface tension as a function of composition, as a function of the concentration of the fluorinated alcohol, and we also measured the light scattering to detect if there were aggregates in solution. And these were the results. The surface tension as a function of composition clearly show two ranges and allow us to determine a critical micellar concentration or critical aggregation concentration, which seem to indicate that there would be micelles in solution, and the dynamic light scattering results confirm this result. Above the same concentration, the light scattering increases considerably, and we could obtain aggregation numbers compatible with the formation of micelles. We did some simulations of this system, and in fact, we could detect in the simulations aggregates, but of equivalent aggregation number. But if you look closely to these aggregates, you can find that they are formed by several layers. A core of fluorinated alcohol in the middle, surrounded by a corona of ethanol molecules, which tend to compatibilize the fluorinated alcohol with the aqueous environment. And finally, a water layer is formed around the ethanol corona. So this is a very complex system in which we could detect experimentally, and the simulations confirm, in which aggregates are formed by an inner core of fluorinated surfactant, stabilized by a corona of ethanol molecules compatibilizing the micelle with the aqueous solution. And this is a close-up view of the micelle in which we have erased some parts of the micelle in order that we could see the interior of the micelle. We also studied this system with xenon NMR spectroscopy, and you can see that in this plot we are comparing the expected behavior if no micelles were formed in green. The experimental data is the black dots, and the simulation data is the red dots. And as you can see, the agreement is remarkable in spite of the complexity of the system. So again, what we are doing is using xenon NMR spectroscopy to probe the organization of the mixture. At the same time, we simulate the mixture, including a xenon atom in the simulation box. Then we observe the coordination sphere of the xenon atom in the simulation, and we calculate from the simulation the composition of the coordination sphere of the xenon atom. And from that, we compute the chemical shift and compare with the experimental results. So in a way, we are checking and confirming that the organization proposed by the MD simulations is confirmed by the experimental results. Additionally, here is a snapshot in which we see the xenon atom inside the micelle, and in the radial distribution functions on the left, we can see again that there is segregation between the fluorinated groups and the hydrogenated groups, in agreement with all the results that I've shown you before. This was recently published in Colloid and Interface Science, and again, it was part of the PhD thesis of Tiago Eusébio, but also Ricardo Luís, who contributed to this study during his master thesis. Finally, the final example is a more drastic one, in which we have bonded together covalently a hydrogenated and a fluorinated chain. This is not merely an academic study. In fact, these semi-fluorinated alkanes are used for many practical purposes, in particular in the biomedical field. Compounds as such are used in eye surgery and to help patients which suffer from dry eye disease. They can be put in as drops in the eyes to prevent evaporation. So for a long time we studied these liquids or these substances mainly in the liquid state and at interfaces. Please understand that in this case we have a very particular type of surfactant because it has no hydrophilic group, but it's formed by two sections which are mutually phobic, but they cannot separate from each other because they are covalently bonded together. They display very interesting interfacial behavior. They can form, for example, micelles in the adequate solvent. They can form liquid crystals, but one of the properties which I believe is the more interesting is when you place these molecules at the surface of water, they organize and spontaneously form amimicelles, that could be detected at the surface of water by atomic force microscopy. This is what I'm showing you here. This is an image obtained by AFM on the surface layer of a semi-fluorinated alkane spread at the surface of water, at the water-air interface. And as you can see, is remarkable because for many years we didn't understand what was forming at the surface, and only when we did some AFM of the films formed at the surface of water, we could understand and realize that they were formed by these surface micelles or hemimicelles, highly monodispersed. And although they seem very small, they are around 30 nanometers diameter, which is very small, but very large at the molecular level. You should understand that in an hemimicelle as such, it exists around 2,000 molecules, which is very, very, very a very large number of molecules. The question then is, why do these aggregates form? Because the molecules inside, there are too many, 2,000. They cannot know that they are inside an aggregate. So why don't they form a uniform layer and they break down into small aggregates in such a regular manner? And for many years, we couldn't understand the reason for the formation of these hemimicelles. At some point, we decided we should do some MD simulations, at least of a small number of molecules, at least to understand how these molecules would orient at the surface of water, because in fact we didn't even know which part of the molecule was in contact with water or facing the air above. And this is what we observed when we did this is an animation, a 10 nanoseconds animation of 100 F8H16 molecules at the surface of water. We are looking from above the water surface. And as you can see, it was very surprising for us to see that the molecules aggregate together and form some sort of spiral instead of dispersing throughout the surface. And as we increased the number of molecules at the surface, larger and larger aggregates were forming until we reached a specific number of molecules, which was in very good agreement with the experimental results, with 2,000 molecules. For example, and the maximum, the structure of the aggregates when the maximum number of molecules had been reached is the one that I'm showing you here. There are three views. The top one, we see the whole aggregate, including the water molecules. If we erase the water molecules, you can see that there is a bump in the middle. This is the top view of the simulated hemimicelle, and here we are comparing the simulated hemimicelles with the experimental ones, and it's remarkable. Not only the size is the expected, but also the small hole, which is not. It's not a hole. It's a well in the middle of the hemimicelle, is present in good agreement with the experimental results. So if we make a cut through the middle of the hemimicelle, this is the way in which they are organized. There is a well in the middle in good agreement with the experimental results. A confirmation, we were obviously very excited and happy with this result, but the confirmation, the definite confirmation that the aggregates we were simulating that we were simulating were in agreement with the experimental results is the following. Experimentally, these films can be studied by X-ray diffraction using synchrotron radiation, obtaining what it's called a grazing incidence X-ray diffraction spectrum. And this is the experimental one on your right. And this is the obtained spectra from the simulation runs. And as you can see, the agreement between the two is remarkable and was a definite confirmation that the organization we were obtaining in the simulations was the correct one. Now I'm showing you another film in which two NMI below the limit size, when brought together, they spontaneously merge each other, forming a single NMI cell, confirming that that there is a limit size with the correct number of molecules below which the molecules tend to aggregate together and form larger and larger NMR cells until the limit is attained. This was published, this work was done by Gonçalo Silva some years ago, a former PhD student, and we published this in 2019 in the PNAS, which obviously we were very happy to with the result. In a more recent work, we could show why this well is forming in the middle of the micelles. We could not understand why this was forming because there were no rational explanation for this well in the middle, but we could show by using different types of force fields that this is due to the interaction between the dipoles that exist between at the cross between the hydrogenated and the fluorinated chain. The different nature of the two chains produces a relatively strong dipole at the carbon atom at the junction between the fluorinated and the hydrogenated chains. And we could show that this is what is causing the alignment of these dipoles is causing this well in the middle at the center of the MMI cells. And this was shown because, as I said, we're using the OPLS force field, which includes electrostatic forces, the well is developed, but if we do the same simulation, but now using the TRAPE force field, in which no electrostatic forces are present, in this case, no well is obtained. And if we use the TRAPE force field, but we specifically add a dipole in the middle, at the junction between the two types of chains, again, the well develops once again. And this was, let's say, an elegant way to show that this is the consequence of the dipole. This also allowed us to develop a model, a geometric model, using the results from the simulations. And in this sequence, I think I will be able to explain you that if you have the central molecule in the middle of the MMI cell, the first molecule that comes around it will align the dipoles, and when the third molecule will come, the dipole will tend to align in this way, and this sequence naturally develops the shape of the MMI cell that we observe experimentally and in the simulations, forming the full developed MMI cell. And this was, let's say, the proof that we were missing to explain the formation of the well. The influence of the dipole was published recently in Colloid and Interface Science, and more recently we published the new geometrical plus electrostatic model in Journal of Chemical Physics. So in conclusion, with this, I finished the examples that I had been, that I wanted to show you. And in conclusion, I hope I have convinced you that the mutual phobicity between hydrogenated and fluorinated chains can indeed be used to generate different types of compartments in supramolecular aggregates. I've shown you Janus-type micelles, onion-type micelles, surfactant-free microemulsions, which are also formed by a complex type of micelle with different coronas, and finally, hemimicelles at the air-liquid interface, also formed by features resulting from the mutual phobicity, which can be considered compartments and then can be used in the near future to dissolve different types of molecules in each type of compartments. And last but not least, I hope to have shown you that the methodology that we developed using Xenon NMR coupled with MD simulations is a very powerful tool to study the organization of supramolecular structures and fluids in general. Before I conclude, I would like to acknowledge the help of a number of people, apart from my direct students, but other people have contributed to this work. Some of them you know very well. First of all, Pedro Morgado, who has been working in my group. He did his PhD with me, and he has been working in my group ever since, and he has contributed a lot to all the work that I have shown you. Luís Martins, a former student who is now at University of Évora. Michel Goldman, who works with synchrotron. He's a specialist in synchrotron radiation from the University of Paris Sorbonne, and also people from the theory and simulations that I've been working with for a long time, like George Jackson, Claire McCabe, and also Lourdes Vega that is now at the Khalifa University at the Arab Emirates, and also João Coutinho from University of Aveiro, with whom we have shared very useful discussions. And with that, I thank you for your attention,